Good afternoon and welcome to the webinar, Getting in Line, Challenges and Benefits of Embedded Measurement. This event, brought to you by Quality, is sponsored by Mitutoyo. I'm your moderator, Daryl Sealand, Editorial Director of Quality. Thanks for joining us. Today's presenter is Michael Crenny, Vice President of Product Management at Mitutoyo America Corporation. Michael brings nearly 40 years of quality measurement industry experience with extensive knowledge of systems and software related to inline and nearline measurement. His focus on future product development has seen him at the cutting edge of metrology innovation and makes him a true expert in the field of precision measurement. Don't forget to submit your questions, and later in the program, our presenter will address as many as possible. Today's event is being recorded and archived on qualitymag.com. And now I'm excited to turn it over to today's presenter, Michael Crenny.
Well, thank you very much for the kind introduction. Again, my name is Mike Crenny from Mitutoyo. I've spent 29 years here in a wide variety of roles, and currently I am the Vice President of Product Management and Sales Solutions, which kind of shoehorns us right into what we're going to talk about today. So this is a little bit about the challenges and benefits of embedded measurement, and we'll move right on to the first slide. So the first thing is embedded as part of the header. It is an object or something actually inside of some kind of cell. And the first question I always ask, do I want to create a system that's inline or embedded? I always ask someone why. There's a number of reasons. The number one, of course, is cost savings. Very important to save costs in today's world. We certainly can see some time savings as well. We'll speed up the process. And then throughput improvements. So all of these together are certainly three of the main factors we want to talk about when we talk about embedded measurement and even line side measurement. So with that being said, we make a definition of, is the application going to be inline or nearline? And those are two specific differentiators. Number one, inline means it's in a production machinery line, and nearline means it's line side or beside the workpiece or beside the actual measurement process. And last but not least, we do want to know what is the required system accuracy. Pretty important when we're trying to push a machine onto the shop floor. And this is a lot of people's goals these days, is to bring it from the current location, which is in the quality lab, out onto the shop floor so that we can actually get embedded and or line side type measurement. We do have a process when we come to look at the entire task, and the first thing we want to do is define the current process. How are we doing it now? So we like to examine the current inspection methods. So we're going to take a very close look at what we're doing in the form of part inspection, what measurements are currently being done, and what are the steps involved in those processes. Certainly the staff involved are really the people that we want to talk to. So we ask the first question, how do we do it now? Who knows how we do it? Probably the most important question, because that person, if it's not yourself, is going to be highly involved in the selection of not only the task, but the equipment, or even to have that thorough, deep knowledge of the process. Are the measurements that we're going to do, are they identified? Do we even know what we're going to measure at this point? What type of equipment is measuring it now? So if we're talking about an inline challenge, are we going to go from a caliper or some kind of hand tool to a coordinate measuring machine or some other kind of device? It's a pretty big leap, and we've got to be real cautious about how we're going to compare and how we're going to contrast what we're currently doing now into a new methodology, because correlation is at the very top of the list when it comes to making sure we're doing it the same and or better. Is the process complete and trusted? That means, do we have an operating procedure? Do we have some standards that we already checked the part to, or even examine these standards so that we do exactly the same methodology? If we're changing tool types, it's probably not going to be the case, but we do have to have a process that our customer trusts, our people trust, and the person themselves actually trusts. So the next part of the identification phase is actually space. And we talk to customers many times. This is a real challenge in today's industry. We've walked into many facilities and there's things everywhere, and embedding a system in the middle of it can be a real challenge. So we want to determine that available space. We want to take into consideration the flow of the measurements of how it's going to be done. Is it going to be done in after process 1 or after operation number 2 or between the grinding operation or the finish operation? So knowing that physical space and how big the equipment is required is really important. We want to consider custom engineering at some point too. Do we have to fit into a certain space, or can we actually allow ourselves to work backwards? So in many factories today, space is at a premium. We find people trying to find the smallest measuring solution possible, almost an exact part fit in some cases. And then we want to choose a wide company. If we're thinking about a coordinate measurement machine, choose a company with a wide selection of measurement sizes that kind of give you some options and help you fit the system into that available space. And remember, it's the shop floor. So dedicated space is always a concern. And if we're coming at it from the quality side, we're certain probably not as familiar with those in the manufacturing side. So when we infringe on their space with measurement products, they really want something that fits their needs and not always the needs of the measurement people in general. Now we want to talk about some of the factors on the shop floor. So always some real challenges on the shop floor. We want to examine that. And the biggest challenges are environmental factors, temperature changes, protection from debris, vibration, and temperature variation is the most significant source of gauging error. So we want to look at a tool that has a wide temperature range and actually has a way to ensure that it can compensate for these temperature swings. So back to environmental, it is a major factor in the entire process examination. Number one, I think, is temperature. Shop floors are not like calibration labs and are not like quality labs. So lots of machines either have to have the ability to change or work to the temperature constraints or adapt to them, or we have to actually think about putting them in an enclosure to keep a consistent temperature. The next one is vibration. When we embed systems, we may find that some of these embedded systems have handling equipment that may come into play, which always cause a lot of vibration. We have to think about machinery. So is it a mill? Is it a lathe? Is it a stamping machine, which is probably the worst machine that we could have for vibration? Cleanliness. Many times workpieces are not in a state of cleanliness. They haven't been cleaned, and we're expecting to actually measure them in line without actually taking the time to talk about cleanliness or even cleaning the part before it actually gets measured. The conditions of the workpiece. Do the workpiece conditions at this measurement process state, Do they have burrs? Do they have porosity? Do they have debris on them, grinding dust? All of those conditions of the workpiece certainly can cause for errors in the system measurement. And the last two kind of go hand in hand here. They're actually fixturing and handling. So fixturing can actually distort a workpiece if we clamp it too much or if we hold it in the wrong way, if it's not orientated correctly. Handling, is it accurate? Does it put it where we need to? Does it put it into a solid fixture? It could actually move it out of position, and then we would slow down or even have an error because we're not handling the part to the proper area. So some of the workpieces that we see in line, actually, the cleanliness seems to be one of the most challenging items. And on very defined workstations and work processes, we actually have a cleaning station that would actually clean the part with a combination of air and or some solution, and then again air, to actually clean the part, and then we have the part presented to us for measurement after it's been cleaned. So all of these above have a great influence on the measurement process, and if there's one step along the way that I could tell you is probably the most important is really examining the factors and the conditions of your part, your workpiece, your floor, and handling and cleanliness. We'll move to the next operation that we talk about, and it is the need for training. So we have to determine what need this is. If we're moving away from the inspection and measurement process in the lab, which is typically by programmers or specialists or engineering staff or in quality assurance, we may need to provide some training for the individuals who will be responsible, and in this case, we'll talk about a CMM on the shop floor. So they may not have the same expertise that the people in the quality side or the engineering staff might have with the equipment. So certainly the need for training must be addressed, and it should be addressed as part of the discovery. So what is our current level? We want to measure that, or at least ask about, do you know how to use this piece of equipment? Have you used this equipment? Are you familiar with this? Where are you in the process of knowing? Could make a big difference on what kind of measurements we get. We always try to examine the most important factors, and some of those factors are, do we have experience or training in automation? If we're going to do a full embedded cell, there is going to be some automation, whether it's moving the part around, whether it's holding the part, whether it's clamping the part, the pick and place procedure. It could be a conveyor system. Again, automation is going to be a factor in an embedded system. What do we know on the floor about metrology? Do we know what makes it good metrology? What makes it good measurement? What happens when it goes wrong, and how do we troubleshoot that? So do we understand the GD&T? Do we understand the measurement routines that are currently in place? So all these factors should help us identify. Again, with automation becomes work holding. Work holding can become quite tricky. Are we going to use the same work holding as the machine tool, which is available in some cases? Or do we have custom work holding that is really for this process and this machine and this measurement task? Do we develop our own? Do we need a partner to actually help us with work holding? Do we understand it enough? And last but not least, certainly, is controls and I/O. So all of the controls of a cell are primarily done with a PLC, but I/O and communicating back from the tool to the equipment, measuring equipment, to the robot potentially, to the handling, to the spraying system, all of these really are controls and I/O, input, output. So do we have any experience with that, or do we need to train on this factor? And I do have one more Monitoring. So in today's day and age, when we talk about Industry 4.0, smart factory, smart systems, and things like that, we certainly want to understand, do we understand monitoring? Do we need monitoring? Do we have shop floor monitoring? Many people have a monitor now that actually gives machine uptime. It gives crash protection notifications. It'll actually help me know which machine is running or where it's coming from. So monitoring is starting to become quite a big deal in even in embedded measurement now. We have to become a node of this overall monitoring platform. And I always say at the end is, ask somebody who knows, or ask what I say is the expert. If you don't know, are you reaching out to the proper company? We'll talk about this a little bit later. But in general, who knows this? Does anyone in our company? And if not, how do we get that knowledge? So next we want to define the task at hand, which is take advantage of new technologies. This may be an opportunity to actually set up a new process for both monitoring and maintenance of the measuring system. We can track the use of this equipment and determine whether it meets the inspections of the cycle and the reduced time. Part of it is to try to take advantage of new technologies. So if you're starting a cell from new, you can investigate the new technologies. They probably will lead to what we call favorable results. So I always ask a bunch of questions. Is there something that's faster? Most likely. Better? Probably. Smarter? Definitely. And then we always say, is it future expandable? Can we add this to another process? Can we use this somewhere else? Can we add more to this? And those things really help us define the return on investment when we're talking about buying a new system or even thinking about integrating a system. We want to think if there's something new that will help us understand that. Certainly we'll want to look to see if something's easier to set up and integrate. And there's always something more plug and play than in the past. The ability to monitor and measure is more prevalent than ever. So if you go buy a machine tool today, or if you buy a production type piece of equipment today, you will get some inkling of how much the monitoring and the measurement and the ability for the machine to potentially send us issues has changed greatly, even over the past 3 or 4 years. All these machines are smart machines now. So in this process, you really should pick a smart machine. So we'll talk about smart systems, explore that capability of smart manufacturing. It may be possible to fully automate the process of identifying errors. So machine tools will automatically adjust based on inspection outcomes. This actually tells us that once we measure, we can sort. We sort by good. We sort by bad. Once we know what this reading is with some consistency and some statistics, we now take this data and we typically filter it because we don't want outliers, and we send it back to the machine tool to actually do offset to improve the machine tool's performance and get us back into a better process. So fully automated systems are becoming the goal for many companies. Smart manufacturing techniques are closing the gaps with increased input, error reporting, uptime, data collection, and automated responsive actions. So not only does it measure, it also tells it what to improve on the other machine tool side as well. So I wanted to go and take a moment to actually talk about the measurement machines that are out in the industry now these are a few of the ideas, not all. We should know that all of these ones are actually do not require air and are very temperature gradient capable. So true what we call shop floor machines. Um, the considerations that we look at, we take the above steps, we get those vetted out, and then we come to some considerations. So what is the system footprint and how does it fit in the cell? Again, back to the pick a machine that fits. There's probably not a lot of space. One important factor is what kind of measurement technique is required. Is it touching or is it scanning? And in some cases, is it even non-contact, which you'll see even later. So many techniques are out there. What I would recommend is, what is the method that we do now? It'll be easier to correlate the studies to the current method than to change the method. However, changing the method of data acquisition, we may turn to a new technology, for us in general, scanning, and it may provide better results and more detail on the measurement system than we had before. So that's the advantage of changing or buying a new system. How does the machine design affect the part handling? The examples you'll see have a wide variety of detail of how the machine is. So some are much easier to load than others. And it is important when you're thinking about robotics and or pallet shuttles and conveyor systems. How difficult are those environmental conditions and what machine will accommodate these? Lots of wide variety in the industry. Some machines, as we know, a common CNC, CMM bridge machine, that machine probably doesn't have the temperature capabilities to sit out in the shop floor. And with embedded machines and talking to the people who actually then control them, which is primarily manufacturing engineering, they want high throughput. They do it on the CNC side, the actual chip cutting, and they want the best throughput for the best machine. But we also consider how heavy the part is and what's the accuracy requirement of the machine. So all of these play into knowing or selecting what type of machine. So now we'll go to a couple of machines here. The machine you see pictured here is in a line. It's actually a cantilever style, and it has actually 3 open sides to it. So this is a machine that's been around for a long time, and it's found favor again because of its ability to be loaded from 3 sides. So it has a what we call a smallish footprint with a good ratio of external size to measurement envelope. So that means it's not much bigger than the size it's measuring. So good size and really open access. So multiple directions on this actual part. It's easy to access, or, and I said integrate, it should say integrate with fixturing and automation. So it has a lot of space. It's less, if you put this up in the home position, you're less likely to crash as compared to a bridge machine. It does allow what we call long workpiece measurement and wide part access. So think of pushing a big, huge part and we're just measuring the tip of a wing of a plane. You could actually fit it in the envelope to measure, which a bridge style would not allow you to. It has usually, and most of what we see today, are hard bearings. So that means it doesn't need air. It's designed with the shop floor primarily as its purpose. So it really is heavy duty and really environmentally strong. And it really is an excellent, what we call near side measurement platform as well. That means that I could load a fixture up with it quickly from a machine tool, hit an execution measurement routine, and then pick that up. One way could be the operator, the other way could be a robot, but a real flexible machine, and now finding favor in the industry. It's resuscitated itself from its real old early design. Some of the problems with it is you must have a really, really solid system. It's got to be high quality design and materials, or the cantilever will actually bow and bend, and there's a lot of inertia that can go on in the y-axis and the x-axis and the z-axis. But it really has to have high stiffness. The design, you should really take a good look at what the materials are. I think that's really important. It does have some accuracy and size limitations. The typical one in the industry today is actually about 500 by 500 by 500 millimeters, which is a pretty good size. But we've seen as big as 800 millimeters. So they're starting to get bigger, but right now you're probably in the 500 millimeter range of measurement. The next concept, or actually machine type, and it is a machine type, is what we call an elevated bridge machine. So this machine is a very small footprint machine, and it can be incorporated in a number of different ways. So this is what we call an internal top bridge type. And with that, I mean, and I don't know if you can see my mouse, but it actually moves its x-axis this way, its y-axis this way, and z stays stationary. So a little different design. Its benefits are it really has a small, safe, space-saving footprint. The one you see here is about 200 millimeters by 200 millimeters. We see them up to 300, so small size, but they really have very, very high speed and high acceleration. It again, because it's open-faced or no really table underneath it in this case, we can put a table, of course, but it allows that long workpiece measurement. So think about taking a shaft or an extrusion and just running it underneath this thing. And as we push it down on some platform, it could just keep measuring the length of this part in infinity. It is an excellent inline or near side application. So we see many people who measure, 5-inch by 5-inch parts all day long. It really does a good job of being an inline machine. It has really high temperature capabilities. This will work from 10C to 40C. So that's what you're looking at. It can be integrated as a node in a larger measurement system. So if we look back again, this entire head can be bolted onto a machine tool, for example, and we could actually move the pallet in the machine over to like a mini CMM, and that's what that is. It does have a small measurement envelope, which is one of its detracting states. It also has no probe index capability, as an index rotation on a probe would probably take up about at least half the measuring envelope. So it's good for its own little things, but not good for everything. I think you'll find that to be the case with many, many measurement devices. The next machine that we look at here is called a horizontal style machine, and this is a really nice kind of picture of what truly people would love to have is a measurement station that has robotic load and unload, and it actually uses the same palletization system as the machine tool. So this is where we start to get to full automation. So horizontal is usually and typically very high speed. The accuracy is terrific because the measurement stroke is not so big. And this is huge acceleration because it's usually linear guides moving on this. So really fast. Some of the fastest machines, CMMs out there, are these type of machines. It is flexible. It has indexing capability, rotary, palletization, and conveyor. So most of the things that you would even try to dream up in an inspection cell would certainly be able to be implemented with this machine type. It's really easy to access from the front and integrate with that fixturing and automation. It really is a machine tool design. You can see the cabinet on the right side looks just like a machine tool cabinet, and that's designed that way in mind. Many of these systems in the industry look like this because their intent is to put them exactly next to a machine tool as part of the overall inline process of measurement and machining. It is an excellent inline machine, and we see it used many times in a very, very harsh factory environment. So some of the challenges with a machine like this is it definitely requires safety integration. The speeds are too fast, the acceleration is so fast, and it's very exposed. It's an arm sticking out in the air, and it really goes quite fast. And we use either what we call is fencing, or we can use light curtain. But we see fencing way more than we see light curtain with this type of machine. There are some size limitations. This arm can only stick out so far before it starts having some bend inertia. When you're moving so fast, it also has some challenges being long and hanging out there as well. And then the last type of machine we'll talk about is a gantry type. So the inner workings of this machine is the X and Y are over the top, and then the Z comes down. This is a pretty solid piece of metal, and it really has few moving parts. It is high speed, high accuracy, and acceleration. It really is a pallet conveyor system. So when we look at it, we're usually shuttling parts from the left side in or the front to back out. So very much a palletization machine more than some of the other systems. It is easy to access and integrate with fixturing and automation. We do it all the time. Many people use this machine to do that. It is a machine tool-like specification, similar to the horizontal machine. We see real hardened bearings, hardened ways, linear guides, and also the control system, which you can't see behind the robot here, is similar to the horizontal machine. It is a cabinet. It is an excellent inline measurement platform. It is primarily built for that reason. It's not built to put in your shop. Again, it usually requires safety, and it's always size limited as well. So next slide we're going to go to, we're at the medium to end point of the presentation, and some of the things that people tend to forget in measurement, we now know about what we should do as a checklist. We then looked at some of the machines and their qualities that may be good for us to embed, but we always have some things we don't think about enough, and I'd like to review those. Certainly the probing. What kind of sensor do we have? Is it touch, scanning, non-contact potentially? Do we have work holding today, or do we need to design new work holding because this thing is going to get moved around in a way we haven't moved it before? Monitoring. Do we have a plan for monitoring? That is very important. In the future, you'll know some of the dashboards you see, we want to be part of the dashboard. I think any measurement system wants to be. Safety systems, we could probably spend a webinar on safety. Think of a measurement tool as a robot. It is a robot, and that's actually how it's classified from a risk assessment standpoint. So many of the measurement machines today are so fast, accelerate very high, that they actually have the same classification as a robot. Next on the list is data collection. If we don't do it today, or if we do it manually, or if we do it haphazardly, we're going to want to have data collection as part of our system. This allows us to do not only machine condition monitoring or machine status monitoring, we also can do measurement data monitoring, which is a big part of helping us determine if we're making good parts real time. You can't do part sorting without knowing part measurement, and data collection is a part of that. Part handling, we talked a little bit earlier about it. Are we going to do it with a robot? Are we going to do it with a pallet? We're going to do it with a shuttle? We're going to do it with a human. So handling is something we could take 4 or 5 sections of and just talk about handling. Part cleaning. Cleanliness is important. Even some of the other challenges of part cleaning is if we scan too much on a piece of aluminum, we're going to pick up debris on the actual stylus or the ruby that's typically used with the CMM. So we've got to understand that what are those methods that we want to keep not only the part cleaning, but it does the part have an effect on the measurement at some point. Machine tool offset. A big buzz in the industry. I would tell everyone, pick an expert. Many people profess to do this, but you need to have an expert do this. We actually have partners to actually do this because they're much better at it than the metrology folks in our estimation. And part sorting could be a pretty complex thing. So if this dimension is equal to this, it's this big, we want to make it go on this conveyor or put it in this bin. And we do have some really high-end examples with some of our customers where it actually knows where to put it. It can put it in a regrind, it can put it in a scrap, or it can put it in a pass-fail. And the intelligence today that you can build systems with allow you to now do things that a human might have a hard time doing if they're not paying attention. And in our estimation, the robot always pays attention. And if you have a really good plan, you can actually sort the part automatically to get it to regrind, or in many cases, we may have parts that are used for certain builds. So all the best parts go to this customer. All the medium parts go to all the 90% of the customers. And some of these parts still can be used for the third customer, and we can sort appropriately when we bring all of these above things or a few of those in place. So how do we choose the right partner? And I will tell you, experience absolutely matters. You really should pick somebody who's done this before. We would hope that you have some internal experience, but if you don't, this is really a challenging operation sometimes. So do they have the expertise to fulfill what your expectation is? After we define what it is, most vendors will be more than happy to come with and talk to you about what your goal is and if you're on the same track as they are. Do they have a dedicated staff to address these aspects, or a partner, one of the two? So some of the considerations that we always ask are, ask the question, do they have their own in-house engineering capabilities? Can they build you a concept fixture? Can they show you a machine? Are they able to design, not only design critical aspects of the whole process, but can they build it themselves, or are they shipping it off to somebody else, or not even able to do it? Could be the question. Can they provide an interactive 3D conceptual model for review? So in our experience and our dealing with many customers, we will build them a cell. They can tell us what robot, what machine tool, and handling other things. And we can actually give them a 3D concept. And boy, this really tells the customer what are they going to get and if they need to make changes, or are they thinking right. But going through the process of developing this 3D model for the customer really allow everyone to visualize processes or components they haven't thought about. So going through the checklist and saying, this is how it's going to work. You can see it for yourself and watch it in action is really beneficial. And I think everyone really benefits from this particular part of the consideration process. And last, do they have proven project management capabilities? All these things are great and well, but if you're not good at project management and actually keeping the project from creeping, there's a word called, or a statement called project creep, you certainly want to be able to have a company who's giving you a Gantt chart, who's talking with you on a weekly basis, who's working you through the issues, who's going back and forth with the new conceptual drawings that that are work holding, for example, but they really need a proven project management. It really helps because everything is clear and everyone talks on the same page. So, and that actually brings us to the end of our webinar today. And again, my data is on the front here, but got through it in a little bit better time than I thought. So I think it's this time we can open it up for some questions.
Absolutely. Thank you, Mike. Yes, as we promised earlier, we're going to take some time and address some of the questions that have come in throughout your presentation. So if you have a question for Mike, I'd encourage you to get that into the Q&A chat. So our first question is from Paul, and he asks, what type of an environment can you use a Bluetooth measuring system, and what distance do you need to go from the gauge to where the data is sent?
So Bluetooth for us is a difficult quantity in a factory. Okay, so isn't 3G. Many of the machine tools that we see today are Ethernet connected, and that's for reliability. But for example, with Bluetooth, there is a lot of noise in a factory. There's a lot of channels. There's a lot of things going on. We know from a hand tool standpoint, we typically have about 15 feet before a Bluetooth signal actually gets disrupted or just is not reliable. In our case, we'd probably at the minimum use a 3G, 4G type wireless connection, as it will go double that at least. So Bluetooth does have some connectivity issues and is extremely susceptible to factory noise. Hope that answers your question.
Okay. Next question. What if you don't have any of these items that you suggest in place and basically starting from scratch? How do I pull this all together?
So you probably want an assessment done. And with that, I mean, if you have a vendor that you're familiar with, or the first one I would do is make sure I know what the measurement process is. And based on how you have that, you may want to reach out to a couple of vendors to say, this is what I expect from this, and help me work through the process. So just like everything else, I always get 3 quotes, right? At least to say, hey, I need some expertise. It's not here. Let me reach out to some of the bigger manufacturers who have some experience, and then let's plan it out with them.
Okay. Our next question is from Arash. Asks or says, we are wave sensor developers and would like to know what you think is the best application for this technology in I guess in their workshop.
So I guess I have to ask, wave is wave sounds to me like microwave potentially, right? So
yeah,
not knowing that completely.
Yeah. Sure. We can ask Arash to follow up on that and see if maybe we can get back to your question.
But if it's a microwave part, right? They typically are small parts.
Arash says it's millimeter wave.
Okay, millimeter wave. Yeah. So similar. It's transmission wave devices, I believe. So these have lots of holes and lots of measurement features in them, and certainly a CMM is probably the best because there's a lot of internal holes. One of the downfalls of certainly measurement with non-contact devices is it can't see through the holes, and it can't tell me things like perpendicularity and parallelism and concentricities and things like that, where a tactile type machine still can do that. And in my mind, they're not that big, so you're probably looking at a cantilever style type machine, harsh environment. It'll work up to 40C, so probably be a good fit. But again, always bring your application to any of the manufacturers, and they'll kind of tell you what machine fits, and based on what you're expecting for throughput, they can help you make that decision.
Okay. John asks, what additional devices or softwares are required to integrate the CMM into a machine cell to acquire and execute machine offset?
So we have a package, and most others do, is have a CMM IO package, okay? And that IO package is basically a generic package that connects to PLC, programmable logic controllers. That's the more integrated way, and that's the hardware way if you're trying to do it with hardware. But there are vendors who are out there who can just take text data of measurement text data and actually send over a network right to the machine tool to do the offset. So the most affordable way is a software solution. There's a couple of vendors out there that do this, and they're very good because they have the one thing with machine tool offset. I said keep it to the experts, simply because they already have the machine tool control data, which we don't have, and which you probably have little knowledge of. They will pull the data, collect all the measurement results, look at those from a control chart standpoint or in and out standpoint, and come up with an average over measurement and then adjust the machine tool automatically. And they are very good at it. They can do anything from lathes to EDMs to mills to grinders, whatever. So again, and he can contact me if he wants, and I can give him a suggestion if he'd like some vendors to look at. Okay.
Okay. Our next question is quite simply, how much does a turnkey cell cost?
So, regular machine could be $50,000 to $70,000. A robot, a cobot out there, you can buy one for as cheap as $20,000 to up to $40,000. A machine tool, $100,000. You could be. It's probably $250,000 if you're to be honest with you, and that would be something that's very sturdy, has part loading, part sorting, even some vision, potentially part recognition, and a robo drill on the other side, right? So it's certainly a high budget challenge. I think a lot of people get talked into some, oh, it's only going to cost you this, and we can use this. This is industrial automation. It's not cheap, but to give you some ideas of some of the basic costs of some of the equipment.
Okay. Next question. They'd like to know what some of the criteria for selecting an automation partner would be.
So the first one, hopefully you have some automation partner in your facility already. If you don't, the best way is to talk to the people that are robotics people. All their integrators is the easiest way to look. They're really challenged by a lot of companies, meaning they're always trying to work with machine tools and measurement people and grinding and cleaning and everyone else. So anybody who's a robot integrator of a high nature, some of the big companies, the top 3 companies, they would be the first place I'd start. Although many people have success with local integrators. So, go to your chamber of commerce, or certainly look around to your other machine shops in the area. See if anyone has some automation in their facility, or even some of your customers, and reach out to those people. They're going to tell you if they've been successful or not, and they'll steer you in the right direction. And again, you can always call one of the. We have people that we recommend every day, and we're not even selling our equipment. We're just trying to give our customers the best people we think can work with them.
Sure. Rosa would like to know what's the best scanner for plastic parts, in your opinion?
Boy, that's a loaded question, but so if it's translucent, it's not a best scanner for plastic parts, but opacity and translucency really set machines off. Right now, if you want my true recommendation, a blue light scanner seems to be the best scanner. Some red light scanners are really good. One, you want to make it sure it's a line scanner. So line scanners cover way bigger area than point scanners, and that seems to be not only the trend but the norm in today. But some of the new high quality, there's some real high accuracy red lasers which blue hasn't achieved yet, but there are some really nice high quality blue style lasers that really seem to do a good job, especially on dark workpieces, which is one of the real challenges with non-contact inspection.
Okay. Next question is, what's the best way to find out about a company's capabilities?
Have a meeting with them, ask them, go visit them. All of the major companies have a solution center somewhere. See if they have a brochure. Most of them, including us, we have a brochure of what our capabilities are. We're more than happy to have you visit or even submit a project task to us. I think you'll know right away who you're dealing with because, to be honest, some of the large manufacturers can afford it. Some of the smaller manufacturers have a tough time bringing it all together.
Okay. Next question. It seems like temperature is a real big factor in getting the proper measurement results. How do these machines compensate for that?
So, from our standpoint, we have temperature compensation built into not all of our machines, but the majority, all of our CNC CMMs. It actually it reads temperature on each axis in 2 locations all the time. We can set the duration. It also has workpiece temperature, so you can actually put one on the fixture and one on the part. And those are real time. The ones on the workpiece and the fixture, you can actually put in the temperature or the workpiece model types. For example, the thermal coefficient of expansion for aluminum is far different than cast iron. And we have the ability to actually do real-time compensation because it's reading the scales of the machine and it's reading the workpiece and its changes as well. I can't tell you how many people want to take apart a piston head, for example, right out of a machine tool, blow it off, put it on the thing, and the part's still hot, and we're supposed to measure it. So how do you do that? Again, lots of these machines now have really good real-time temperature compensation of both the machine to keep that environment stable and the workpiece, which I think is really important to know that you should have both.
Okay. That looks like just about all the questions that we have today. So please join me in thanking Michael Crenny for his presentation, as well as our sponsor, Mitutoyo. If you have any additional questions or comments, please don't hesitate to click on the Email Us button on the console. Please visit webinars.qualitymag.com for the archive of this presentation, as well as information about our upcoming events. We appreciate your time and hope you found this webinar to be a valuable experience. Have a great day.